This is the next video in the chapter on electronic structure and periodic properties. We are talking about the second periodic property, which is ionization energy. So ionization, that's a new word for us that we haven't really talked about yet. Ionization is removing an electron from an atom completely, moving it so far away from the nucleus that it isn't technically associated with that nucleus anymore. So the ionization energy is the amount of energy required to move an electron. And when these values are measured, they're specifically measured for gaseous atoms. There we go, amount of energy we need to remove an atom. So if we draw a Bohr model of the nucleus, remember we drew sort of circles around for each successive energy shell. N equals 1, N equals 2, and if we want to be lazy, we know that there's more and more and more shells up to the top of the paper. Eventually, if we increase high enough, we reach a value of N equals infinity. So this is the farthest possible distance away from the nucleus where the electron could be. And at this point, at N equals infinity, the electron is so far away, it can't see the positive charge anymore, and it is free. It is no longer part of that atom. It has been removed. So the general trend for ionization energy is as shown in the picture here. It is a larger positive number towards the right, and it is a larger positive number towards the top. So it's the exact opposite of the trend of atomic radius. So let's dive into why that is. So it's sort of like the transition from some n value to the n equals infinity value. So the electron is moving up from some level to the top. And remember, this is going to be an energy input process. Some energy in the form of a photon is going to be required to promote that electron up to a higher level. So a photon energy is going to be required to remove that electron from the atom. So another way to call the ionization energy, an easier way to think about it, is it's a measure of how strongly an atom resists becoming positively charged, becoming a cation. So we can write the process for some generic element X. We represent ionization energy with IE, and you can remove each electron in turn. So this is the first easiest to remove electron is IE1. So if we had an atom of some element X that is a gas, its ionization would turn X into X plus the cation, and an electron that's no longer associated with that atom. And we can remove each electron from a nucleus in turn if we try hard enough. So we could take that positively charged cation, and we could remove another electron, creating a 2+ charge. So that's IE2. And this continues depending on how much energy you have available to you. These are the kinds of radiation that we drew in our ionization energy spectrum that are the dangerous kinds. The ionizing radiation are the kinds that do this to atoms in your body, because your body does not appreciate having its electrons removed. But we should note each successive ionization requires more energy than the last. So we already have to put in energy to remove the first one, which is the easiest one to remove. But as we continue to remove more and more electrons and create a stronger and stronger positive charge, it takes even more energy to remove the next and the next electron, because that's pretty unfavorable for most atoms. Okay, so to think about what this number means, because students often get confused about the large number, meaning it's more unfavorable, let's spell that out here. So if we have a large, very positive value for the ionization energy, this means that the formation of a cation from this element is unfavorable. So there's a large amount of energy input necessary to make that cation happen, and large energy situations are unfavorable. The opposite is true. If we have a small positive ionization energy, that means the formation of the cation is favorable. It still takes some energy to pull that electron away, but it's a much smaller amount, and so that's a favorable situation. So let's try and explain the horizontal and the vertical trend for this periodic trend. We will do vertical first, as we did for atomic radius. So what happens as we move down a group in the table? So as we do that, we're adding a large number of electrons and protons at a time. And so those electrons are put into the next shell much farther from the nucleus. And when we put the electrons farther from the nucleus, there are more trees in between them and the nucleus. It's more difficult for them to feel that positive pull. So Z effective for these outer electrons is smaller than it is for some of the inner electrons. And if the effective nuclear charge is smaller, that means that it's easier to pluck off those electrons on the outside. The pull they feel to stay in that atom is not as strong, and so it's easier to pull them off. So if we wanted to summarize the trend, our positive ionization energy is going to decrease as we move down a group. The larger those atoms get, the easier it is to pluck off an electron from the outside because they're so far away from the center, the atom barely notices it's gone. So the largest ionization energy is at the top, in those smaller atoms. All right, so far so good. Let's do the horizontal trend now, moving across a period. Right, so as we move across a period, we said each step involves the addition of one proton and one electron. So we add one proton to the nucleus and one electron, and that electron goes into the same shell this time because there should still be space as we move to the right in the table. Whereas here, when we moved down a group, we added so many electrons, we were moved into the next shell. Moving horizontally, we're adding them to the same shell. So if we're adding the electrons to the same shell, they don't have much of a shielding effect, but we did add a proton, and that increases the positive charge. So the effective nuclear charge increases because we've added more protons. So if the effective nuclear charge is larger, if the pull of that nucleus on the electron is stronger, that means it's going to be harder to remove an electron. They're more attached to each other, and it's going to be harder to pluck off the electron because it's still kind of attached to its spot at the edge of that atom. So we can summarize that trend. Ionization energy is going to increase across the period. It's going to be harder and harder to remove that electron as we step to the right, so the amount of energy it takes is going to be higher. So the largest positive values for ionization energy are going to be at the right end. The largest values at the right and at the top. So let's have a look at the trend. If I can find the sheet of paper where it is. There we go. So you should be able to see at least a general trend here. We said we're expecting to see an increase as we move towards the top of the table, or rather as we move down, we expect to see a decrease. So we can look at the noble gases here, helium, neon, argon, krypton. As we move down the table, we see a decrease in ionization energy. And we said as we move to the right, we expect to see an increase in ionization energy. So here's an example of one period: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. As we move to the right on that row, the value generally gets larger. So those major trends are true, but if we zoom in and I hold this a little bit closer, you can see that the line isn't perfectly straight. There are a couple of little zigzags inside of this trend, specifically between the group 2 and group 3 elements, and between the group 15 and group 16. There's a little dip in the trend. So let's think about why that might be. So beryllium is in group 2, and things that are in group 2 have an electron configuration of 2s2. That orbital is filled. And then when we step to boron is in group 3. Its 2s2 is filled, and it has the first electron in the 2p orbital. So that reason that step was different was because we were moving from this filled 2s subshell to putting a new electron in a new previously empty subshell. So that's going to be a reason why this step between group 2 and group 3 doesn't exactly match the trend. And then let's look at this other trend. This is between our group 15 and group 16. So over here in group 15, we have a filled S subshell. And in our P subshell, group 15 is going to have 3 electrons in it. So it's going to be half filled. And for group 16, like oxygen, the 2s subshell is going to be filled. And the 2p subshell, we are going to be adding that 4th electron. So it's going to be the first time that we have to double up electrons inside of that p subshell. And that's what makes this energy slightly lower, is because it's easier to ionize this 4th electron because we don't really want it here. It likes being half filled better. So this is the first time that we've seen this. So we had better stop and take a moment and write this down. Because no matter how smart we think we are, we can't argue with experimentally collected data. So there were a couple of anomalies that we saw in that trend. It wasn't just a simple increase. It had a couple of zigzags in its shape. So the first zigzag occurred when we were going from a filled shell to an unfilled to filling the next shell, or rather an empty shell to a filled shell. So filled and empty subshells are more stable, meaning they're lower in energy. So if we have something here that was the first one to fill that empty subshell, it's easier to ionize that one because it would return us to this preferred, more stable state of being either totally filled or totally empty. The next anomaly we saw was this bump over here. And that was about changing our half-filled subshell. First time we had to double up and pair electrons together. So we learned that these half-filled subshells are slightly more stable. The bump wasn't quite as big, but it was slightly lower in energy, so it was slightly preferable. So here, The bottom of this bump was the first time that we filled up, we doubled up in a particular orbital. So the ionization energy for that was slightly lower because it was more favorable to remove that one because it would set us back to our favorite half-filled orientation. So those are our two anomalies that we saw in that trend. And the last trend that I'd just like to mention, we talked here about how each time you ionize an atom, it requires more and more energy. And there, if you continue to ionize an atom, there's going to be a significant difference between one value and the next value depending on the atom. So when all of the valence electrons in the highest shell have been ionized, the next ionization step is going to take way more energy than the one before it. And that is because you're no longer removing a valence electron, you're removing a core electron. And those core electrons feel a much stronger positive pull. So this is like if the first ionization took 500 joules and the second ionization took 1,000 joules, and that was the end of the valence electrons. If your next electron was a core electron, then that next ionization might take 4,000. There would be an extra large jump between the last valence electron being ionized and the first core electron being ionized. So in the next video, we will talk about the last periodic trend, which is electron affinity.